As you remember from our previous discussion, positives and negatives attract. So let's go back to our example of electric fields. Say we have a uniform positive charge that's a point, and then we have field lines coming out from it. And as we get farther away from the charge, the field lines become shorter, which represents a weaker field. The arrows of the electric field, they represent the direction that a positive charge is going to be pushed if it is placed in this field. Longer arrows represent a stronger push or force. So if we place a positive charge here, it's going to be pushed with a large force this way. But if we place a positive charge here, it's going to have a force pushing it this way, but it's going to be a smaller force. Now there's also another concept I want to introduce. That is that in metal, which we know is a conductor, charge can move freely. You may not have heard the term conductor before, but conductor means that charge can move freely. So we're going to draw this point charge again, right here. But we're going to put a metal object or conductor around it. Here it is right here. So now we're going to draw our field lines again. And just like before, the field lines come out of the positive charge. But the thing is, what happens when these field lines run into the metal object? I went over just now that in a conductor, charges can move freely. So negative charges are going to move to the positive charge because positive and negative attract one another. But like I went over in a previous section, whenever you have a change in charge, an equal change in charge must occur. Net charge must always be zero, which means we must have positive charges over here. And because we have positive charges on the outside, the field then continues. So, it looks very similar to the electric field of a charge without a metal object, with a metal object. But the difference is that there is not an electric field within the metal object. You're probably going to be tested on this actually. Note that there is never an electric field within a conductor. Now there is actually a practical application to this situation. Imagine we have two equally charged plates of opposite charge. One is positively charged, the other is negatively charged. But we're going to have a rectangular prism. Imagine it's a hollow box, but it's a metal hollow box. And here it is, right here. So, if the metal box was in here, field lines would move across, positive to negative. But just like in the previous situation, negative charges meet the positive charge, and positive charges meet the negative charge. And there is no electric field within this open space right here. And this is called a Faraday cage. Faraday cages are often used for high-tech electronics to make sure that if a sudden electric field appears, if there's some large radio signal that's sent out, that the electric device will be protected because electric fields will not be able to reach it because it's in this hollow space.